Picture this. You're running a recommendation system at Meta, and you want to suggest items to a user based on what similar users have engaged with recently. The raw graph of who engaged with what has, conservatively, hundreds of trillions of edges. You need to learn embeddings on this graph, refresh them every few hours to keep up with fresh content, and serve recommendations to billions of users with latencies measured in milliseconds. Most academic research on graph neural networks pretends none of these constraints exist. Most industrial systems tackle one piece of the puzzle while leaving the others unsolved. The paper we're discussing today, called RankGraph-2, argues that the only way to make this work is to stop treating graph construction, model training, and real-time serving as separate problems, and instead design each one to satisfy the constraints of the others. The motivation is grounded in a very concrete observation. At Meta's scale, three things bite you simultaneously. Building the full co-engagement graph is infeasible because of its sheer size. Training a graph neural network on it normally requires specialized online graph infrastructure with distributed sampling engines that traverse multi-hop neighborhoods at training time. And serving the resulting embeddings through approximate nearest neighbor search over a constantly changing pool of recently active users would require thousands of machines. Prior industrial systems each chip away at one of these. Systems like GigaL and LiGNN build heroic infrastructure for in-memory subgraph sampling during training, but they still serve through approximate nearest neighbor lookup and assume someone else built the graph. McGNN compresses the graph by clustering nodes into macro nodes, which is elegant but blurs out the precise structure around niche users and tail items. Generative models like OneRec sidestep graph structure entirely by predicting next items autoregressively, which captures temporal intent well but misses the explicit multi-hop collaborative signal. Here's the central insight. The authors notice that for similarity-based retrieval, meaning user-to-user-to-item and user-to-item-to-item flows, the underlying signals are structural and relatively stable over hours. They don't change second by second the way click-through rate prediction does. That observation unlocks everything. If neighborhoods don't need to be sampled fresh during training, you can pre-compute them offline. And if you pre-compute them offline, you can do operations that would be impossible online, like running multi-hop personalized PageRank over the full graph and applying popularity bias corrections. So the requirements cascade backward through the pipeline. Serving says, I need a cluster index instead of online nearest neighbor search, which means training has to co-learn that index. Training says, I want self-contained edge-centric data with pre-computed neighborhoods, which means graph construction has to deliver that format. And construction says, fine, but I also need to finish in under an hour because serving wants fresh items every 3 hours. Think of it less like a relay race where each runner just hands off a baton, and more like designing the runner's shoes, the track surface, and the handoff zones all together because the constraints of each leg dictate the others. Let's walk through what construction actually does. They build a heterogeneous graph with 3 edge types, all derived purely from engagement data, no external social or knowledge graph. User-to-user edges connect 2 users who engaged with at least some threshold number of common items in the past day. Item-to-item edges connect items engaged by overlapping user sets. User-to-item edges come directly from interactions, weighted by engagement value. The popularity bias correction is worth pausing on. If you naively count co-engagements, popular items dominate everything because they show up in everyone's history. So they re-weight item-to-item edges by dividing by the popular item's total edge weight raised to a small power. Intuitively, if you co-engaged with a very popular item, that's weak evidence of similarity, like discovering 2 people both drink water. Then they aggressively subsample, prioritizing high business value nodes and keeping only the top edges per node by weight, which brings the graph from hundreds of trillions of edges down to hundreds of billions. Finally, they run personalized PageRank with a Monte Carlo random walk approximation to find each node's structurally most important neighbors at multiple hops, and they package these pre-computed neighbors directly into edge-centric training records. The whole pipeline finishes in about an hour. The training stage is then, almost shockingly, just standard supervised learning. Because every training record carries its own neighborhood, there's no distributed graph engine in the loop. The model is a heterogeneous aggregator with multi-head type-aware encoders for users and items, producing embeddings by combining a node's own features with aggregated representations of its user and item neighbors. The loss is contrastive link prediction, combining a margin ranking loss and an info NCE objective, with negatives sampled 3 ways: from other edges in the batch, from a rolling out-of-batch pool, and through multi-head augmentation where different attention heads provide alternative negative views. The hyperparameters that weight these losses are learned through uncertainty weighting rather than tuned manually. And because the batch sizes are now deterministic without unpredictable graph traversals, GPU utilization stays high. Now for the most novel piece, the co-learned cluster index. At serving time for user-to-user-to-item, instead of doing approximate nearest neighbor search over the dynamically changing pool of recently active users, every user is assigned a hierarchical cluster code, and each cluster maintains a real-time queue of items recently engaged by its active members. A retrieval becomes a simple lookup in the queue for that user's cluster. The trick is making sure clusters group genuinely similar users. They use residual-quantization with 2 codebook layers, so each user gets a 2-level code that together identifies one of roughly 250,000 clusters. Critically, the codebook is trained jointly with the embeddings with a reconstruction loss, ensuring the quantized embedding stays close to the original. But residual quantization under continuous training tends to suffer codebook collapse, where a few codes get used constantly and the rest atrophy. They counter this with 2 complementary tricks. A regularization loss tracks how often each code has been selected in the last 1,000 batches and penalizes the current batch for reinforcing already popular codes. And during code assignment, they apply a biased selection that softly favors underused codes. Think of the codebook like parking spaces in a busy lot. Without intervention, everyone piles into the spots nearest the entrance, and the rest stay empty. The regularization is like dynamically nudging drivers toward emptier sections so the whole lot gets used. The result is 100% codebook utilization and serving costs that drop by 83% compared to online approximate nearest neighbor search. The experimental results back up the co-design thesis quite forcefully. On user embedding quality, measured by recall of next-day engagements, RankGraph-2 hits a recall at 5 of about 14%, compared to under 4% for a graph attention network with Deep Graph Infomax pre-training, and just over 1% for HSTU, the sequential foundation model. That's a 3.8 times improvement over a more architecturally sophisticated graph model trained on a simpler bipartite graph. On item embeddings, RankGraph-2 reaches recall at 100 of 0.775 versus 0.374 for PyTorch-BigGraph, a 2.1 times gap. The ablations are telling. Adding user-to-user and item-to-item edges on top of the basic user-to-item bipartite roughly triples recall. Using personalized PageRank neighbors instead of random or top-weight neighbors lifts recall at 5 from around 5 or 10% up to 14%. Popularity bias correction adds meaningful gains on item embedding quality. And the codebook regularization is the difference between a learned index that nearly matches the original embeddings on a hit rate metric versus one that drops substantially. In 14-day A/B tests across 2 surfaces, the system delivered up to a 0.96% click-through rate lift and a 2.75% conversion rate lift, and has powered over 20 retrieval launches at Meta. The authors are reasonably honest about limitations. The whole approach is tuned for similarity-based retrieval where structural signals dominate. For direct user-to-item retrieval, ranking models that use real-time behavioral features are still more effective. Pre-computing neighborhoods means you can't do query-dependent neighborhood exploration, and the 3-hour graph refresh may be too slow for extremely time-sensitive scenarios like breaking news. There's also an implicit assumption that engagement signals contain enough information to derive all 3 edge types meaningfully, which may not hold in cold start settings or smaller platforms. And the broader claim that simpler architectures plus better infrastructure beats more complex models is empirically supported here, but may not generalize to every retrieval setting. Now, let's walk through some questions you might have after hearing all of this. First, why does moving neighborhood computation offline actually improve quality rather than just matching online sampling? The intuitive answer is that online graph sampling is constrained by latency. You typically can only do shallow walks or single-hop sampling because you need to feed batches fast. Offline, you can run full multi-hop personalized PageRank over the entire backbone graph, apply expensive popularity corrections, and pick the truly most structurally important neighbors. So offline doesn't just match online quality, it exceeds it because you've been freed from latency constraints. The trade-off is that your neighborhoods are slightly stale, but for similarity-based retrieval, the structure changes slowly enough that this barely matters. Second, how does the cluster index actually replace nearest neighbor search without losing quality? The key is that the cluster assignment is co-trained with the embedding objective, so users in the same cluster genuinely have similar embeddings by construction. At serving time, finding similar users reduces to looking up which cluster a target user is in and reading items from that cluster's queue. You're effectively doing nearest neighbor search once during training, baking the result into a quantized code, and then reusing it cheaply forever. The codebook collapse defenses ensure clusters stay diverse enough that any individual cluster is small and tight, preserving the similarity guarantee. Third, why use 3 edge types instead of just the standard user item bipartite graph that most recommendation systems use? The ablation shows each edge type contributes complementary signal. User item edges capture direct preferences. Item edges capture content similarity, which helps long-tail items that don't have much direct engagement. And user edges enable serendipitous discovery by routing through similar users' histories rather than just similar items. The bipartite-only baseline gets a recall at 5 of about 5%, while the full 3-edge version triples that. The cost of constructing the extra edge types is amortized offline, so you pay once during the hour-long build and benefit during all subsequent training and serving. So how does this transfer to the kind of large-scale recommendation system you might build at any platform serving hundreds of millions or billions of users? The most actionable insight is that for similarity-based retrieval flows, you can probably eliminate your online graph sampling infrastructure entirely and replace it with offline pre-computed neighborhoods, freeing engineering resources to invest in graph construction quality like better edge weighting, popularity corrections, and multi-hop importance sampling. That alone can shift the quality frontier without touching the model architecture. The co-learned cluster index is also directly applicable wherever you do user-to-item retrieval over a freshness-filtered pool. Instead of maintaining a fleet of approximate nearest neighbor servers and recomputing indexes constantly, you train a quantized cluster assignment once and serve from cluster queues, which is dramatically cheaper at high query volumes. More strategically, the paper makes a strong case for thinking of recommendation systems as a coupled lifecycle rather than a stack of independent components. Production teams often have separate orgs owning data pipelines, model training, and serving, and each one optimizes locally. The biggest gains here came from letting serving requirements rewrite the training objective and letting training requirements rewrite the construction format. For platforms where graph-based retrieval coexists with sequential or generative models, Treating these graph embeddings as structural prior features into your ranking models or even into your foundation model representations is a clean integration path, since you've already paid the cost to generate them and they carry collaborative signals that pure sequence models tend to underweight.